Hey, we're back! Alright, well now it's time to start talking about variables. Variables are, very much like what you would work with in, say, a math class, where like x is equal to 3, or pi is equal to 3.14159, or x is equal to y plus 2, or something like that. You can have equations and so on. Variables are the same kind of idea. Now, I like to think of variables as being a little place in the memory of the computer, like a little box, and we can put something into that little box. I don't tend to think of it that way in mathematics for whatever reason, but like here's a little box in memory, a little place that I'm going to call x, and I'm going to put something into x, and x will be a place that is storing that. And because that is in fact physically pretty close to how it actually works on the inside the computer itself, that helps you think about how computers, what kind of steps you need to go through to work with a variable. And one of the things you have to know about a variable in any kind of computer programming language, Fortran, Pascal, NCL, whatever, is that it has a type. Type is a word that we use to describe the nature of the information that's going to be stored in this variable. Now in practice in this class, we're only going to be working with a few very common types of variables. One type of variable is going to be an integer, and another type of variable is going to be what C calls a floating point number. Integers are counting numbers. Rabbits. You can have 7 rabbits, you can have 8 rabbits, you can't really have 7.5 rabbits. Floating point numbers are measurements. They go, 1, 2, 3, no, 1, 1.5, 2.5, 3.5, 4.5. I mean, they have decimal places to them. This is a very important distinction because, in fact, the computer, inside of its memory is actually storing these numbers very differently. So it has to know x is going to be a floating point number versus I is going to be an integer or whatever your numbers are. So maybe, like, for example, you have a variable called temperature Fahrenheit. Okay, temp F, let's make it simpler, temp F. That's a floating point number. It's going to have, it could be 32, but it could be 32.1, it could be 32.01. In fact, even when it was 32, it's really a measurement. I mean, it's not exactly 32. That's in contrast to an integer. Maybe you're counting number of stations that report this hour. That could be a perfectly good name of a variable. It's a horribly long name, but let's just say number. Number, that would be like storing how many. You can't have 2.5 stations report this hour, and you can't have 2.01 stations report this hour. It's either 2 or it's 3. Okay, so you have to know when you're working with your variables, are they going to be an integer or are they going to be a floating point number? And the very first thing you do in your program, right below main, is you have to so-called declare these variables. Before you can actually use a variable like x, or tempf, or number, or whatever it's going to be, you have to tell the program you're going to be working with this, and you have to tell it what kind of variable it's going to be. Because behind the scenes, inside the computer, what's really happening is it's setting aside a little place in the memory of the computer, and it's calling that tempf. And it's defining that that is going to be a floating point number. And it's giving the computer the instructions as to how to format that area of memory so that it can store a number with decimal points and so on. And so what we do is up at the top of the program, before anything happens, we declare. Now in practice, that's just good habit. In practice, you can actually declare the variables elsewhere in the program, but you'll lose them. You'll never figure out where did I declare tempf? No, it's very good habit to have your variables declared up at the top, right below main. They do have to be inside of the curly braces associated with the main function. I just lied to you. There are in fact situations where you would declare them outside of main. That's called a global variable, but we're not going to work with global variables in this class because they're bad. They're a bad programming style, and your future employer would hate it that you even know such a thing exists. So what we're going to do is we're going to declare. Now, so up near the top of this program that I have here on the screen here, I have declared some integers, I and j, and I've declared some floating point numbers, temperature and pressure. The integers are declared using the C command int, int, And then after that, we have another one where we're declaring some floating point numbers using the command float. And so in this case there, we have two variables, I and j, that are going to be integers. At some point we'll have decided what I and j are or whatever. I'm just making a program here. Obviously, we'd be more likely to have a variable named something like number of contours to draw or number of stations or something like that. But I and j are fine, okay? And you can put a list of them there, like I have two, so I made I, comma, j, that's fine. There's two variables I'm declaring here. Or I could have done them on separate lines. I could have said integer I, and then on the next line I could have said integer j, int I, and int j, that would have been fine. Same with like the floating point numbers that I have declared there. I did them on one line, but I wouldn't have had to. I could have had float temperature, and then the next line float pressure. And because these are commands, they have to end in a semicolon. So actually what I would have had to do if I had made these on separate lines is I would have said int I, semicolon, int j, semicolon, float temperature, semicolon, float pressure, semicolon. Hey, one thing I've been meaning to tell you on the way here is make sure that you understand blank lines have no meaning in C. You can have as many or as few as you want. I mean, they're just there, those blank lines are just there to help your I keep parts of the program separate. Okay, so then below here, I just started using the variables to just do something. Now, this is not a particularly interesting program. Here I just gave an example where I showed like my integer I. Hell, I'll just set it equal to something. I is equal to 3. Or temperature, I have a variable there called temperature, and I'm just setting it equal to 98.6. Again, because those are commands, we're doing something, they have to end in a semicolon, as C lines always do. One of the things we might want to do with these variables at some point is print them. We might want to know what is in this variable. Now, when this little program that I have right here, let me take a look at this little piece of it here. I declared an integer called WSPD, which is how I always write wind speed. I mean, you could write out wind speed, or you could do whatever you want. It just can't have a space in it or anything, but as long as it's just letters, it's fine. Here I set the wind speed equal to 10. It's an integer. This was actually very foolish of me. Wind speed is not an integer. Wind speed is a floating point, right? It's a measurement. It can be 7.1 knots out there, or it can be 10 knots or whatever. But I'm just demonstrating right here. So if I wanted to actually print the value here, we have to modify our idea of what a printf statement can do. Now, here in the little blue box, I'm showing you the result here is it printed out the word, the wind speed is 10. And how did we do that? Well, I have now made some changes to the business going on inside of my printf function. My printf now is actually getting 2 arguments. Previously, we were just having one argument where we would say, like in quotation marks, this is the weather channel, /n. Now I have 2 arguments. One is a string, a set of characters. And it says, the wind speed is %d ./n. We'll come and parse that all out in just a little bit. And then comma, and wind speed, my WSPD variable. There's 2 arguments. 2 pieces of information are going off to this function. One is this set of letters, the wind speed is %d, and the other is this variable, WSPD. What's actually going to happen here is that we separate these 2 arguments using a comma, and %d is what C calls a format specifier. Again, this is something any computer language you're working with is going to have these things. They might be slightly different, but they're going to work the same way. What's going to happen is when the printf statement actually starts working, and it's going to write to the screen, the wind speed is, when it hits %d, it will replace that %d with whatever are the contents of WSPD, the wind speed variable there. So that first time that it hits a format specifier, in this case %d, it's going to replace that with the contents of WSPD, because that's the next argument. So that's why we got this output that says the wind speed is 10. Because 10 was the contents inside of the WSPD variable. %d is the format specifier for an integer variable. If you've declared the variable, like in this case WSPD, using int, so it's an integer, %d is the format specifier that matches up with that. So when you have a %d in your printf statement, it's looking for, it's expecting the value inside of WSPD to be an integer. Okay? We could have done this with floating point numbers. In fact, it would have been far, far smarter. If I had declared WSPD to be a floating point number using the float WSPD command, and then I had set wind speed not equal to 10, but to 10.0, okay, it is a floating point number, it has decimal places, then our format specifier for a floating point number is %f. That makes you wonder, why was it %d for integers? Everybody has wondered that since C was invented. I'm sure there's a perfectly reasonable reason why %d is used for integers and %f is used for floating point. The second one makes sense. Why %d? Actually, %i works as well for integers, but it's kind of a hack. It's a trick. The formal way to use a format specifier for an integer is %d. And so if you go back here just real quick and look at the output here, it says the wind speed is 10.00000. It's a floating point number. It's expressing to you that there's, to high precision, we know that the wind speed here is 10, because I just told you that. We could make this tidier. I hate it when floating point numbers have all those digits way out past the decimal point. We don't measure the wind speed out to, millionths of a meter per second. Why do we have it? Why are we keeping track of all these decimal points? So, for example, you can put a number between the % and the f in your format specifier. In this case, like 4.1. %4.1f means your floating point number can only be 4 digits wide, and with one of those digits to the right of the decimal point. So like in this case, I changed the print statement to be the wind speed is %f, and %4.1f, and now when I write the output it says the wind speed is 10.0, because it's saying I can only use 4 digits and one of them has to be to the right of the decimal place. That can make your output look a lot tidier on the screen. You can put any combination of numbers there. I mean, like for example, %9.6f means that your floating point number is 9 digits long. 6 of them have to be to the right of the decimal place. So like if I wrote here on my screen here that the wind speed is 9.6 wind speed is %9.6f, then the variable wind speed gets put into that format specifier in 9.6f format. That means 9 digits wide, 6 of them to the right of the decimal place. There is actually another little trick you can use. If you don't really care how wide the number is, you just care how many digits after the decimal place, you can just write %, like for example, %0.6f. And that means I don't care how wide the number is, but I want 6 places to the right of the decimal place. So here I modified my print statement to be the wind speed is %0.6f. And then what we actually get back in output is the wind speed is 10.000000. I'm getting 6 places after the decimal point. Again, if I don't really care how many digits there are to the left of the decimal place, which frankly is most of the time, that can be a powerful tool. Unsurprisingly, C knows all of the mathematical operators. In practice, no, it doesn't. But once you've pound included math.h and you have linked to the math libraries with the -l thing, then it does know all these things. So % minus star for multiplication is star, slash for division, pow with a comma b as its arguments means a to the b power, is all it's all possible. Sine, cosine, tangent, all that kind of good stuff. It knows all that kind of stuff. Once you've pound included math.h and linked to the math libraries. So like a typical kind of thing you could do in C is like, if you have a value in a variable called y, then maybe x could be equal to 5 plus y. Okay, that sounds like a perfectly reasonable command to issue in C. Now, we're going to come across this problem several times in the class, but I want you to start noticing something. We actually use the word equals in English kind of weirdly. There's actually several ways in which we mean things that we call it equals. X equals 5 plus y is not a math problem in this case. What we're saying is set the value x equal to 5 plus y. Whatever's in y, add 5 to it and stick that into x. Okay? So when the computer program hits that line, it goes and looks for the value of y, takes that value, adds 5 into it, and sticks that into x. If x had a value beforehand, that value has been clobbered. Believe it or not, that's the technical term for that. that value is gone. Okay, so if previously x was equal to 0, and now, I don't know, let's just say y was equal to 1,000,000, x equals 5 plus y now means that x is equal to 1,000,005. And the old value of x, it is gone. It has been clobbered. So read this word equals here to mean like is set equal to. Now, again, this is a place where students often get tripped up. If later you change the value of y, like if on the next line the value of y changes, that does not change the value of x. Okay? It's not like these variables are somehow linked the way they might be in a math class or something like that, or in a physics class. In an atmospheric science class, potential temperature is equal to some blah 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 blah, and it has the temperature in there. Okay? If you change the temperature, potential temperature changes. That's not what's going to be happening here. This is more like a calculator, okay? When I read x is equal to 5 plus y, whatever the current value in y is, it'll add 5 to it and stick it into x. Whatever happens after that to y, x doesn't care, okay? X is now equal to what it is equal to, or you can feel free to change now x is equal to z plus 20, I don't care. Also notice it always works this way. The left-hand side of the equal sign is what's getting changed. The right-hand side is what's the math that's going to get done and then put into the left-hand side. Man, I remember when I was first learning programming a long, long time ago in a different computer language, it happened to be BASIC. I didn't understand that, and I could never figure out what my programs were doing wrong. If I had this the other way around, 5 plus y equals x, mathematically that's fine, but it doesn't work in computers. The one you're changing, the one you're setting equal to this is the left-hand side. The right-hand side is the other one. Now, programs have to have notes in them. Especially as your programs get longer and longer. All these programs we're going to be doing today are not very long. But they're going to have notes in them. That note, the word that explains what the program is doing, what bugs there are, etc. That's called documentation. Okay? This lecture's gotten long enough. This assignment is hard enough. We're not going to worry about how you document your programs. We'll do that in a different day. So, what's going to happen on this assignment? I'm going to go back to my prompt here, and we're going to practice this stuff about variables in a little bit. But what I want you to do is I want you to do some calculations like, and this comes from page 35 in your textbook, you're going to do things like convert 15.3 Celsius to Fahrenheit, or write your program. You're going to make a program called something like assignment3.c or something, or homework3.c, that's fine. I think we're on 3. And you're going to make a program that does all these things. Okay, compute the potential temperature in Kelvin of this air that has this temperature and this pressure. Compute the potential temperature from, whatever, all these different things. Convert a wind speed from knots to miles per hour, stuff like that. And you're going to print the results of these calculations to the screen. It might sound like a lot, but I can tell you, even 2 assignments from now, you're going to think this is baby stuff, okay? It doesn't change the fact that I realize your first time it's a real challenge. So let me go ahead, bust out of this here, and I want to show you what I'm doing here. So I'm back here at my screen on Chesapeake, where I'm logged in as student 315, and I'm going to just go back and open up sample.c again, pound include math.h, pound include stdio.h, main, and there's my angle brackets. Okay, so let's just do some examples of this sort of thing. In fact, why don't we do something similar to what was in that first part of the problem, where we are going to be converting a temperature from Fahrenheit to Celsius. Okay, and I'm not even going to go look at what the actual problem is, but we're going to be taking a temperature in Fahrenheit and we're going to convert it to Celsius. Temperatures are floating point numbers. They can be 37.6 degrees just as easily as they can be 37 or 38, right? So they are float. And I'm going to go ahead and create 2 variables. I'm going to create a temp F for the temperature in Fahrenheit and a temp C for the temperature in Celsius. Now let me tell you what I'm doing here. I have been writing programs for like 20-some years now. Oh my, it's longer than that. Wow. Anyway, Anyway, I have long since learned that making the variable's name tell me what the units are as well is a really handy thing. I mean, here's the deal. I could have called this temp 1 and temp 2, or I could have called it temperature Fahrenheit and this is my dog, all run into one word or whatever, but that doesn't help me. Making the variable's name tell me what's in the variable is a useful thing, but I could have called this anything I wanted to. In fact, I'll demonstrate that in just a little bit. But making the last part of the variable's name tell me what the units are is just really good habit, okay? Because otherwise, you've got a number in there. You've got a variable called temperature, and it has a value in there of 10. Is that Celsius, Fahrenheit, Kelvin? I don't know. So that's not so easy. So let's just say I'm going to convert a temperature in Fahrenheit. Maybe the problem told me to take body temperature, 98.6, sorry, 98.6. So temp F is equal to 98.6. And then I'm going to say temperature in Celsius is equal to, and then let's do the math. Well, how do you convert a temperature in Fahrenheit to a temperature in Celsius? Well, it is the temperature in Fahrenheit, and I realize I'm doing some things here that we haven't yet talked about. I'm using parentheses, for example, which is fine. You take the temperature minus 32 and you multiply it by the number 5/9. Now, I realize there's a couple of things going on here. Let's actually look at this for a second. Temp C is equal to temperature minus 32 times 5/9. Yes. Okay, the parentheses here are necessary, right? The subtraction by 32 has to happen first. Feel free to go, by the way, for the assignment in general, you'll need to go to the appendix of the textbook, which has that common meteorological calculations chapter, which is really, really helpful for such things. In case you don't actually know these equations off the top of your head or know where to find them or whatever. So temp F minus 32. Now, I could have said temp F minus 32 like this, where the integer. Temp F minus 32. But that's actually not technically correct. I'm not taking this floating point 32, let's say my temperature is 32.5, and subtracting 32 an integer, because, degrees aren't something you just count, right? They're something you measure. So strictly speaking, taking a float minus an integer doesn't work. Now, as it happens, GCC is smart and catches that error most of the time. So it would actually go ahead and change 32 to the floating point number 32.0, and it would catch it for you. But it doesn't always, and it's just good habit. Sometime later in your life when you're working with something else, Python or Fortran or something like that, the compiler, well actually Python doesn't have a compiler, but that's another story. But at some point along the way, like the compiler or whatever won't necessarily know that. Or if you're using a different C compiler than GCC. So it's just a good habit. In the same sort of way, multiplying this by 5/9, I could have done 5 divided by 9. And GCC is pretty smart, it might have caught that. But here's the deal, 5/9 is actually a floating point number. We're not saying take 5 rabbits and divide them among 9 dogs and you get 0 rabbits per dog with 5 left over. This isn't remainder division like what you would do with an integer. This is a floating point. I want the result to be 5/9, which I believe is 0.55555. So to do that, it needs to understand that 5/9 means 5/9. 5.0 divided by 9.0. Okay? I know, that's kind of messy and hard to think through, and we're going to catch that error lots of times in this class, okay? Keeping track of the differences between what do I mean? Do I mean that to be a floating point number or do I mean that to be an integer number is a tricky, messy thing. I'm going to show you one more little detail you can do. Strictly speaking, you don't actually need a 0 there when you have like 32.0. It could actually be just 32 point, and this could be 5 point, and this could be 9 point. In fact, I've noticed when I was flipping through the textbook that there's lots of places I did it that way. So this would work just fine. Let's actually print the result. Printf %f Fahrenheit is %f Celsius /n. I'm actually doing something a little bit different than we did in the little lecture part here. I'm actually making 2 things print in part of here. There's going to be the temperature in Fahrenheit and the temperature in Celsius. By the way, I was just messing with there. Notice there were little spaces between the arguments that didn't hurt anything. Those little extra spaces, they didn't hurt anything. So what's going to happen here in this line here is when the printf hits this first %f, it'll replace that %f format specifier with the first argument, which is, well, I guess second argument. Let's be clear about that. This part in quotation marks here is the 0th argument. Then the first argument is temp F, which will go into the first format specifier, and then the temp C will go into the second one. They just go in order like that. Alright, let's see if this works. I'm going to hit escape to get back into command mode. I'm going to hit colon WQ to get back into write and quit. And I'm back to the Unix command line. I'm going to say gcc sample.c minus lm to link to the math libraries. And it doesn't look like anything happened because it didn't hit any errors or anything. So if I type ./a.out, I get wait, I told it was 98.6. Yeah, but 98.5999998 is really, really close to 98.6. We're hitting a precision error problem in the computer, but we'll talk about that in a different lecture. But that works out to 37 Celsius. Oh, that's neat. Let's go back into our program and see if we can mess around with it. I didn't like all those decimal places there. What I really wanted was this out to like 1 decimal place. Well, I can change my format specifier of my temperature in Fahrenheit will be %.1F. That'll be 1 digit to the right of the decimal place. And let's do the same thing for the format specifier for the temperature in Celsius. It'll be 1 digit to the right of the decimal place. I'm going to escape and get back into write and quit. I'm back to the command line. I have to recompile the program because I've made changes to the program, right? There is still an a.out. Look, if I type ./a.out, I still get my program. But that's the old a.out, right? I need to make a new one by recompiling. Again, I'm going to just use my bang G command to recompile. And then ./a.out. Oh, isn't that nicer? 9.8F is 37C. Now, we could have done... So this is what I want you to do. So like on your next part, let's say your next problem involves converting... So like this would be like, I don't know, here's your part 1. And then maybe like in the next part you need to compute a potential temperature. I'll call that theta K. Okay, so we make a floating point number called theta K, and then farther down here you'll have theta K is equal to and whatever it's equal to. Okay? You can do these things like that. It'd be no problem whatsoever. I want to show you a couple of things that would have worked. I could have called temp F something totally different. How about T1? Now I'm going to pull a trick here in VI. I'm actually going to use global search and replace. At some point I'll teach you all about this. To replace all of the temp Fs with, let's just say, T1. Okay, and I can do the same thing again here. I'll take all the temp Cs out and replace them with T2. Alright, so instead of having temp F and temp C, I've got T1 and T2. T1 is equal to 98.6. T2 is equal to T1 minus blah blah blah. Printf, this is here, temperature T1 will go into the first format specifier. Temperature T2 will go into the second one. I'm saving it and quitting. I am recompiling the program because I've made changes, and I run it and it works just fine. But what a piece of junk of a program. I have no idea what T1 and T2 mean. Now, if I actually had documentation or notes in my program that would help, maybe I could make this work. Maybe. But it's way better, I'm going to use that global search and replace that you don't yet know how to do, to go ahead and put those back the way they were. I'm replacing T2 with temp C. See how that just makes the program make a whole lot more sense? And the same way, I mean, I've had students over the years who want to use variable names like puppy and goat and dog. Unless you're talking about puppies and goats and dogs, don't use variable names like that. That just causes confusion. Variable names, though, do have to just be one string of letters. You know, you can't have spaces in there. Temp F wouldn't work. Okay? In general, don't use special characters like $ and dots and ampersands and stuff. All those things generally have special meanings in C, and it'll be confused as to what it thinks you're doing here. Just use strings of letters, like TEMPF is a lovely variable name for temperature in Fahrenheit. Okay? So this is basically what you're going to be doing on this assignment. And now, let me just look real quick. I had made myself a set of notes about assignment 3, and I put them in this directory. Let me make sure I told you all the things that you need here. It says here, the students need to know that the steps in your program happen in order. Oh, students need to know that they can reuse variables. I didn't mention that. I mean, my guess is you know it, but let me go back into sample.c. I'm doing this wrong. Sample.c. There's absolutely nothing wrong here with now saying tempf equals 0. Using that same, I'm actually going to just use cut and paste to put that same equation in here. Temp C is now equal to temp F plus, oh, well, let's actually do this here. I'm going to go ahead and put the same print statement here. Alright, so what's going to happen here is temperature in Fahrenheit is set to 98.6. Then temperature in Celsius is this conversion. And then we're printing the results. Then I'm changing the value of the temperature in Fahrenheit. Temp F now contains this number, 0. Temp C is set equal to 0 minus 32 times 5/9, and we're going to print it again. Let's see if that works. I'm going to use my little shortcut there to compile. I'm going to run it. 98.6 Fahrenheit is 37 Celsius. 0 degrees Fahrenheit is negative 17.8 Celsius. That sounds right. So see, there was no harm in reusing the variable once we were done with it. As long as I didn't care that I was clobbering the old values of it, it didn't actually hurt anything. But, well, you know what? It's worth pointing out. Let me show you one more thing here. Let's say I didn't have this line right here. Okay, so what happens in my program? I set temp F to 98.6, temp C is this conversion. The temp F and temp C both have numbers in them. Then I print those numbers. Then I'm setting temp F equal to 0, but I'm not going to do any calculations, and I'm just going to write that again. Temp F is equal to temp C. So in other words, there should be a mistake here, right? Temp C is, we didn't change it. Temp C still has the value associated with 98.6 Fahrenheit. Well, let's go ahead, write and quit, compile, and run this bad boy. 98.6 Fahrenheit is 37 Celsius. 0 Fahrenheit is 37 Celsius too. Wait, that can't be right. Because see, I didn't change the value of temp C. I need to go back in here, and again, I'm going to use my tricky cut and paste function that you may or may not know how to do yet, but I'm going to do it just to save some time here. So now, temp F is set to 0, temp C is recomputed, plugging it into temp F and all that kind of stuff again, and now when we save, compile, and run the program, it works just fine. 0 degrees Fahrenheit is equal to negative 17.8 degrees Celsius. Let me go back and check those notes again one more time. Assignment 3.text. We know how to go to the end of the line, know about the dot at the end of floats that look like integers, I know about that. Know that the declaration should be at the top of the program. They need to know about converting to knots and meters per second. All those conversions are in the back of your textbook.